Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about small modular reactors. So let's dive right into it. Now first, why we are dealing with this? Well, first thing we have to understand that we have to reduce our CO2 print now, CO2 footprint at this point in time. For example, the way we are continuing our power generation, it has to change. It's not optional anymore, it's compulsory. So that's the primary motivation behind this technology. Then nuclear is one of the options that we can utilize. Not everybody does like it, but it is an option. Now, if you want to solve all our world's problem with solar, yeah, that's not gonna happen. But if you want to do solar plus wind, now we are talking. Now if you want to add solar, wind plus thermal, geothermal, awesome. Solar, thermal, geothermal, hydropower, and then let's say wave power and tidal power. Now you're talking about taking care of it. It's like done. So that's way we are talking about the power mix. Like you want to mix all these sources. One of those sources that everybody is excited about is nuclear. One of the primary reasons for this is that it is stable. Like you put it, you turn it on, and you forget about it. It's like, yeah, I'm getting 10 megawatt power out of it. I'm getting 300 megawatt. I'm getting 50 megawatt, whatever case we are talking about. You're getting that amount of power. That's it, the end. You don't have to think about it. It's like you're gonna get that amount of power, and it's very long term, as in like even a normal basic power plant can easily work for 2 years without needing any refueling or shutdown. And if you specifically design it, for example submarine power plants, those can easily stretch to 12 years without needing anything. Like you turn it on, come back to me after like 12 years. So that is fundamentally very awesome. Now if you may like, okay, if it's that awesome, why the heck we are not building it everywhere? So biggest problem is it makes sense to make it big. You want to, rather than making 20 megawatt, 30 megawatt, you want to make it like say 1000 megawatt, 600 megawatt. So like big boys. Now that is the biggest problem. Like if right now you want to go there and figure out how much time and how much money these puppies will take, that's insanely high. For example, many nuclear power plants, they have been started, and to give you a context of this, India started to work on thorium power nuclear technology the moment we got independence. Like that was like one of the first things. It's like, no, we need energy independence. Thorium, we have thorium reserves, let's start working on this, let's try to figure it out. Nothing in physics is stopping us, just we have to figure out the engineering side of it. We did even started to build a reactor, like a prototype reactor. We started to actually build it. Now here's the deal. That reactor should have been ready, working, prototype level on 2012. I'm making this video in 2021. So you get the point. Like it takes insanely long amount of time. Now because of the time it takes, the money department also goes up. So like for example, US will be like, okay, this nuclear power plant will produce this much power for this much year, and we think let's say $8 billion should be good enough. $8 billion for 7 years. Okay, everything is good, everything is go, project is green, everybody started working. It's 12 years and the plant is nowhere near completion. It's already consumed $12 billion. So you get the point. It takes very long amount of time, and it takes insanely large amount of capital, and many times projects can be flat out abandoned. It's like people like, dude, I can't keep sunking money into this. That has happened. That's why that 12-year long period, that's way too long. You want something that is very quick. It's like for example, when India was building one of its largest solar farm, we were achieving quote unquote 1.5 megawatt of power applied every day. Like that's how quickly we were growing. Like compared to nuclear would be like 12 years divided by the power plant capacity. That is very slow. So fundamentally it takes too much and too long. Small modular reactor supposed to solve this issue. Now let's understand what's the logic behind it. If big can't solve it, like how can small solve it? The first idea is, first we will make it small. Why we will make it small? So we can ship it rather than manufacture it. Right now every nuclear power plant is manufactured on site. Very few things are brought somewhere else. Like the main reactor, they are like actually built there. Okay, the containment building, we're gonna build it there. The main system, the main as many things as possible is built there. Like products are brought there, like of course fuel rod and all that. It's like, but it's like custom built on that location. So that idea would be thrown out. The idea is you're gonna make it as small as possible. Basically it should be road transportable, like how Falcon 9 is. That's the core idea. Make it road transportable. An ideal world, it would be transportable inside a normal container ship within the normal weight limit. So it should be like just ship it, like Amazon 24-hour delivery. That's the whole point of it. And this will be simple. We will not try to achieve like very high complexity or like as fewer parts as possible, and it should be safe. Now, these three core components make a small modular power reactor is something attractive. The reason is we can be able to mass produce it. It would be much cheaper if you can mass produce it. Why? Simply think of this way. You have one mega factory that is making these things. All they are making is like they're gonna give you one unit. Let's say one unit is 100 megawatt. You're gonna order as many as you want. You're like, hey dude, I'm only gonna power this city. It does not consume too much. 100 megawatt is more than enough. You're gonna order one unit. Somebody like large metropolitan, they're like, dude, give us like 500 units. They're gonna give, of course you're not supposed to put 500 units in the one place. Of course you have to distribute it out. So of course it will also help you to reduce electrical waste because of the large power lines. So you can do that. That's the whole point of modular. You're supposed to pack as many as you need based on your power requirement. So if you need exactly, let's say 200 megawatt, you get a reactor that only gives you 200 megawatt, or you add up two small ones that gives you that much power. So that's the whole point of modular. And everything on this puppy is designed in such a way that complex part, the reactor part, that has to be very simple. So you're gonna order the reactor, it's gonna come to you, and then you're gonna attach systems to it. What kind of system we are talking about? Basic normal steam circuit systems, nothing fancy, and it won't be basically radioactive, so you will not need shielding, and everything that needs to contain the nuclear system will be in this unit. That's the whole point. The reactor itself is contained in one unit, and you can add as many as you want. So another aspect would be, let's say you build a large plant, and right now we make very huge reactors. Each reactor could be easily 1000 megawatt. Now consequence of that is, the moment you have to refuel it, and it could take upwards of 1 month to do this all process, you are talking about shutting down 1000 megawatt from a national grid. That kind of drain is very painful for national grid to recover from. So they generally try to like plan it out very thoroughly, and then they're like, okay, this power plant turbocharge every system, get every backup generator you have, like make it all work. Every coal power plant, go YOLO. Hydro power plant, do you have water reserves? Go YOLO. Like all of them have to go YOLO, then only you can shut down the reactor. Otherwise, like you will literally blank out half the states. So fundamentally, having multiple small units gives you the advantage that you can serialize it. It's like, okay, I'm going to take away one unit. Let's say it's 1000 megawatt plant, you will only take away 100 megawatt. That's a minor dip. It can be managed. And that time you're going to refuel it, service it, whatever you have to do, and then you're going to plonk it back into the service. Done. Then you're going to do it serial wise. So rather than having like one giant dip, which is also bad for financially, because if your power plant is not producing electricity for 1 month, you're not making money for 1 month. So you can, that's the whole point, like simplify the finance aspect of it, make it simple, cheap, effective, and safe. That's the logic behind it. That's why we want to mass produce. Like we're gonna have one giant factory, and it's gonna ship as many as you want. And based on buildings, containments, and all that jazz, that would be done with simple concrete, no fancy lead shielding and all that. So that's the whole point of it. Now, what's about the design aspect of it? Design aspect is solely focused on one aspect, like one thing, get this done properly. That is passive, safe, auto shutdown. Right now, many people think that you can shut down a power reactor. Well, technically true, it's practically untrue. What does that mean? That simply means, yes, you can stop a nuclear reaction from happening the moment you insert control rods. Awesome, everything good. But still we are dealing with nuclear stuff, and it will remain hot for days. Sometimes you would be, you could easily see things like remain so hot that it takes 2 years in a cooling fuel. Basically, you take spent fuel, you have to cool that spent fuel for 2 years. So you get the point. Like if your reactor is, let's say, producing thermal energy of, let's say, 500 megawatt, you shut it off, it will not go from like 500 megawatt to 0. It will go from 500 to 200, but it's going to remain in that 200 for a very long time. And design is the biggest hurdle with the Fukushima plant. It shut down, everything was done safely, but because backup systems were off, it needed active water cooling for it to remain in that safe state. That safe state was not safe. It needed constant energy, and all these things are designed in such a way that A, if something bad happens, it should automatically shut down. So at least if boom happens, it should not happen at 500 megawatt, and B, it should not need any active system for safing the reactor. After reactor shutdown, it should not need it. Basically, this is the reactor, you press the big red button, shut down, it's shut down. Nobody should need to touch this. That's the whole point. It should not need water supply. It should not need, which was the main fault with Fukushima. It's like the backup systems failed. Everything was there, everything was planned, but again, if backup system fails, your reactor is fundamentally, even in off state, is dangerous. That should not happen with this. That's the primary objective of this. It's like automatic off. If something happens, earthquake, power failure, something happens, the end, shut it down. Second, it should automatically cool itself down enough where it's like, I can forget about it. It's like shut down, done. Not like Fukushima. It's like the engineers are rushing, like, dude, get the backup generator, get it as quickly as possible. Otherwise, we simply gonna have a boom explosion. And they did have boom explosion. So these are the two primary objectives. How they are achieving it? Again, there are hundreds of design on this, and very few designs are actually in quote unquote final stages, and only two, as far as I could find. And one of they are very close to actually being made, but these two are. And primary interesting idea is that you're gonna have control rods, and they're gonna have electromagnets. So the moment you have power failure, the electromagnets is just gonna drop it. So these kind of things are there, and they're generally gonna use simple pressure water reactor. Now you may be like, why the heck you want to use water? What about molten salt and all that? There are some designs that are utilizing that, but benefit with water system is that it's gonna take the heat from the core and it's gonna turn into steam. They're gonna be emergency relief valve that works on pressure. It's absolute system. We know that it works. So pressure is gonna increase. Let's say PSI was designed for 500 PSI, and it goes beyond that. Let's say 600 PSI. The burst is burst, and then it comes outside. Now these all things are happening inside the main container material. Like that's why you will see there is like cone inside a cone. Then it's gonna steam is gonna come out. It's gonna drop in temperature, and then it's gonna collect in the bottom. Then from the bottom is gonna drain into core again. So this loop will continuously cool it down. So it will go from, let's say, 500 megawatts of thermal energy to 200. The moment you turn it off, that 200 is gonna quickly shut down on its own. That's the whole thing. It should not need a coolant pump, backup pumps, recovery pumps. No. On its own, it's gonna utilizing convection itself. It should cool it down to a point where it's like it's off. You do not have to think about it. It will not melt through the casing. Nothing bad will happen. It's like that's the whole thing. And generally, for legal reasons, is classified as any single unit should not produce more than 300 megawatts of electrical equivalent energy. And there is micro reactors also that are like generally a few megawatts, 1 or 2 megawatts. Now you may like, is it worth it? Well, for military, they are like, shut up and take my money. Now, are there any drawbacks about this? Well, we still have to deal with nuclear waste, and biggest problem with nuclear waste is no matter how little you make it, it's just like you're still talking about making sure it's safe for hundreds and thousands of years. That's flat out impossible with humans. Like that's why we are having such an issue with nuclear power plants. That's why not everywhere in the world we have nuclear power plants. It's like everybody wanted to do that, and before we had the events of Chernobyl and all that, everybody wanted a nuclear reactor. So why didn't we get it? It takes so goddamn long. People are like, dude, my government will be like, if a government legislation is like, dude, you want to build a power plant, awesome. How long it's gonna take? Dude, my grandchildren would be there. So flat out, we are not really good at for long-term thinking. And this puppy requires insanely, like on an evolutionary time scale, it needs kind of maintenance. Flat out, we can't deal with it. And then some people will say, what if we make it nano diamond batteries? A, nobody has actually made it. B, anytime you see a CG rendering, run. That simply means the product is not real. And not to mention, doing anything in lab is child's play. Doing anything in real life, 99.999% of thing fails. So that's the whole thing. And even if we successfully make it, it's so low power that best thing we're gonna do with that is make it into pacemaker, make it into hearing aids, anything that goes inside human body. So and not to mention, every Tom, Dick and Harry claiming this system is safe. How do we know it's safe? Because saving something like classifying something safe has to happen over time. It has to happen like saying that this rocket is safe and you only launched it once. That's not acceptable. You have to launch it 10,000 times and then be like, okay, none of those 10,000 times it had any accident. Then you can say that. That's why air industry is classified as the safest mode of transport, because it's like, if I'm gonna move 100,000 people every day, then only 0.001% of people will gonna suffer loss of life, and this will be over a year. So that's fake. Like unless not every Tom, Dick and Harry is used like right now, most things are in design phase. How the heck you can call it safe? Only 2 reactors have been built and they are not old enough to be classified as safe. So fundamentally speaking, not enough time has passed to classify as safe, because I can give you a simple example. Like they have this containment, they have electromagnet in the pipe, and the pipe is gonna drop it. What happens if pipe bends for any reason? Let's say it has a pressure explosion, pipe bent, your electromagnet idea is locked, or earthquake happens. Some severe earthquake can literally move like a steel rods like this. So that things like of that nature does happen. That's why if not enough time has passed, we cannot classify it as safe. And solar and wind are already cheaper. At this point in time, more and more people are building solar farms simply because it's financially viable. Nuclear was not viable back then. How the heck is going to compete against these things? And these things are continuously dropping in price. Fundamentally, like you can see the price curve, it goes like tick, 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 tick. It's like right now in my hometown, it's more financially viable to like have a solar based system rather than to just pay the electrical bill. It's like literally cheaper. So that's in my hometown, and more people are doing this. Everywhere people are doing this. And if you mix that power, like that's what I'm saying, like solar alone is not gonna solve our problem, but you mix it with wind, you mix it with hydro, you mix it with geothermal, you mix it with as many things as possible, and I'm talking all renewable systems. We can take care of basically earth right now. And battery prices are also dropping fast. So think of this, like few years ago, if you had told anyone that you're going to have a Tesla power wall that's going to take care of your house overnight, used on the based on the solar itself, and it's going to cost however it's cost, is like, let's say half price of a car, people laughed at you. It's like, dude, that's impossible right now. And the way price is dropping, I am hoping that by the time, let's say 5 or 10 years from now, price would be equivalent to let's say a washing machine. It's like, yeah, almost a washing machine level price, same size, and it's going to take care of your house. So when that happens, at that point in time was the end game of a small modular reactor. Every Tom, Dick and Harry can run on solar, and your grid can have a wind as a backup and biomass plants as a primary system, so you can turn it on and turn it down, remove intermittency. Biogas systems can happen in the basically towns, because we humans produce lots of bio waste. So there is a lot of options. So the biggest thing I can see in this system is that it may not be cheap enough. Then what is then? For example, every company that is working on, they are saying the proper commercial use cannot be happen before 2030. That's the biggest. Then 2030, what happens in 2030? What if these things are keep going down continuously? Then what? So fundamentally, I do not see too much magical application as people are talking about this. So is there what we can expect in the future? Well, in marine environment, this puppy is gonna shine. Why? We have a track record. There is knowledge, there is information, there is actual experience data. Is like, what happens if you put a nuclear reactor in a submarine? What happens if you put a nuclear reactor in aircraft carrier? What happens if you put a nuclear reactor in icebreaker? So we have experience. We know like how long, 30 years, 40 years, we have this kind of experience. So we know for a fact that we can make marine reactors safe. And there is another benefit. Let's say for every shipping containers we have shipping systems that we are utilizing, they start to utilize these puppy, and one of them went boom. Now, worst case scenario, it goes completely boom. It happened away, as far away as possible. Now, hope that this sort of thing does not happen inside a port, but even in ports are not generally populated city centers, quote unquote, nor it's a very close area. And let's say it happens on an ocean, because most of the time ships in ocean, it will dilute very quickly, reducing the risk to public. So fundamentally, there is some good hope there. And to give you a context of why would you want to do this, is like, think of this, if I average out what kind of fuel consumption we are talking about, 1 ton to 60 ton fuel, 16 tons of fuel per hour per container ship. So you can get the context of it. It's like, it's not consuming liters per hour or gallons per hour, it's consuming tons per hour. If that kind of carbon footprint can be removed, and given the fact that we know how to do this, we have been doing this, that's awesome. That's like everybody wins. Heck, that reduces the shipping cost. Primary shipping consumer is like ship's capital cost and the fuel cost. If fuel cost goes down very low, and you may be like, oh, isn't uranium expensive? The amount we use is so low, and actually speaking, uranium is very cheap. So fundamentally speaking, there is a lot of hope in the marine environment, lot of hope. Like for example, why does US spend so much over, like compared to a diesel based system, nuclear based system is so much more expensive. The nuclear aircraft carrier, the primary reason is the space it saves allows all their ships, basically all the aeroplanes on it, to have like almost 3x the more range capacity, simply because they have, the ship itself has empty space that can be filled with jet fuel. So that's the whole point. That's why people, military is so excited about this system. And small reactor for remote area, for example, Russia is already doing this, where they have a plant. It has like around, it's not too GG powerful, but it's like 100 to 200 megawatt kind of power, and it's just like ship is docked into a docking area, and then just power plant done. So that's kind of awesome. In those sort of scenarios, in these two scenarios, I can easily see this technology becoming like a backbone level technology. But everywhere else, every like Tom, Dick and Harry, it's like it's gonna be way of the future. I don't see it, because by 2030, and God help you if somebody figures out how to make a dual junction solar panels which are having efficiency of around 30%. Yeah, God help you at that point in time, and if it's cheap. So this was my presentation on small modular power reactors. Hopefully you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.